Okay, this is the solutions for Chapter 10 quiz on probability. Question 1 asks the probability of getting all heads in 3 coin flips. One way you could do this is to write out the entire sample space. In other words, write out all possible options. So you'd start off heads, 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 tails, heads, tails, heads, tails, heads, heads, and so on. If you list them all out, there will be 8 possibilities. It's equally likely to get any of them. So one of those is all heads. 1/8 would give you this decimal. Another way, probably an easier way to do it, is to think about each flip individually. On each flip, you would have a 1/2 chance of getting a heads, and because the results of one flip doesn't impact the results of any other flip, they're called independent, we can just multiply the chance of getting a head on each individual flip, and there's 3 flips there, giving us a total of 1/8. Number 2, so we wake up healthy for about 95% of our life, and if we randomly select 200 days from our life so far, about how many of these days did we wake up healthy? So if we woke up 95% of the time healthy, that would be 95% times the 200 to give us 190. On the flip side, 5% that we woke up sick or hospitalized, something would be 5% times 200 would give us 10. So roughly 190 healthy, roughly 10 sick. And of course, those are estimates, and any given random selection of 200 days may be a little bit off on those numbers, a little bit higher or lower. Okay, randomness, you've seen this concept come up quite a bit in random sampling and random assignment. So this one is asking about random sampling. Remember, this was typical in observational studies, not very common in experiments, just because it's very, very difficult to take a random sample and then make them do an experiment. But the power of it in sampling is that it produces a sample that's representative. So this helps you generalize then to the population. You find some results for your sample, and you can say, well, probably these results would hold in the population as a whole if you've done a random sample. If you do a convenience sample, then you can't necessarily make that jump from your sample back to the population. Okay, here now we also have random, but this is random assignment. Once we already have the people in our study, and the randomization process is more about putting them into one of the groups, that's the assignment process, and that helps balance the groups on basically every variable you can imagine, even the ones you don't think of. So it helps control for the lurking variables. Again, not perfectly. We know that random chance can always be a little bit off, but it is predictable in the long run. Okay, here's a poker. You certainly want to read the question here. I'm just going to go straight into the answer. But a 2-pair, chance of that is 1/21. So something little less than 5%. So A is not correct, almost certain. So any given set of 21 hands may or may not contain 1 2-pair in it. This is where randomness in the short run, we can never be certain. It's always unpredictable in the short run. In the long run, this one is really close. The issue here is 1 2-pair for every 21 that are not 2-pair. What this is saying is out of 22 hands, one of them would be a 2-pair. So this would be 1/22, and it's a common misconception of what 1/21 means. This means 1 2-pair for every 20 that are not 2-pair. So one of them's 2-pair, 20 are not. That gives you 1/21 chance of getting a 2-pair. Again here, so even if you have a lot, we can't say that the number will be exact. What will be closer and closer to this 1/21 probability will be the actual percentage or probability that that you get the number of pairs that you should get. But the specific number is not ever going to be right on the dot. Deal thousands of hands, fraction very close to 1/21st, so that is what we can assume. So this is not the number of hands, but it's saying the fraction, the portion of them, the percentage of them that are 2 pairs should be very close to that theoretical probability. And then this is just the complement rule. So if we know that the probability of getting a 2 pair is 1/21st, then the only other option is to not get a 2 pair, and so that would be 1 minus 1/21st, which would give us 20/21st. So here we roll 2 dice and we win if it's either 10 or higher, or if we get doubles. If we take a look real quick at the probability model, you can count the doubles here. 1, 2, 3, 4, 5, 6 of our 36 are doubles. But then we also have the 4 6s, the 6 4, the 5 6, the 6 5. So there's really 10 possibilities there. If you use the overall sum rule, you could say probability of doubles is 6 out of 36. Probability of 10 or more is 1, 2, 3, 4, 5, 6 out of 36. But then you'd have to subtract the overlap, which is the pair of 5s and the pair of 6s, because they're 10 or higher and they're doubles. So we'd subtract that out. Either way, we're going to get 10 out of 36 would be considered a win. And if we divide that out, that would give us 5/18 or 0.278. Here we're rolling 3 dice. What's the chance that at least one of the 3 lands with a 6? So the reason you can't just say, okay, let's do 1/6 chance for the first dice, get our 6, and then 5 6 times 5 6 to not get a 6, because it doesn't say that our first roll has to be a 6. We just want at least 1. Whenever we have an at least 1 situation, it's usually easier to get the opposite. So first to calculate what's the chance of not getting any 6s. In that case, to not get any 6s, we'd have to get a 1, 2, 3, 4, 5 on each of our rolls. So on the first roll, we'd have a 5 6 chance. Second roll, we'd have a 5 6 chance. Third roll, we'd have a 5 6. They're all independent. None of these rolls impacts or affects the other rolls. So that would give us 125 over 216. That's our total chance of getting 0 6s, getting no 6s in our 3 rolls. But since we want the complement, we want the opposite of that. We want at least 1 6. We just subtract this from 1 to get 91 2/16, or as a decimal, 0.421.